Hello friends, welcome you all for the 31st session of Mobile Development. So in the last lecture, we saw the programming tools, a brief overview of what are the development environment and target environment is about, and then we briefly touched upon the procedure call standard, and then I gave an example also using a C function, and then how parameters are passed through some registers into a function, and then how the return value, the return result, whatever comes out of the function is passed back to the call function, and how the stack frame is used for creating space for local variables, as well as the arguments which are passed into the function using the frame pointer. So in this lecture now what we are going to cover and see a little bit more about the linker. Okay, why I am taking linker so specifically is that is where you may have to tweak based on the memory map of the target hardware. Okay, so how to place a particular software, is what you develop for a hardware. So what are the things you need to be aware of? So it is a bit vast subject. It won't be possible to cover them all in this lecture. But my intent is to give you enough introduction and the features that you need to be aware of, so that you will be able to read the documentation that comes along with the tools and development environment, and you will be able to develop the software for the system that you are building, which are ARM based, which are the systems which are ARM based. So once you are aware that these are the things you need to be cautious about and where to look for what kind of information, then it will be easier for you to develop any software system you can build using the ARM based SoC. Okay, so having understood about what is inside the processor, now we are little bit spending some time on the tools and what needs to be taken care of by configuring the tools. Those things we are now trying to look at in this two lectures, and then we'll again go back to some hardware related stuff, peripherals and other buses in the subsequent couple of lectures, and then I will conclude it with the giving some details about various families of ARM processors and which are the advanced features that are there supported in them. Okay, so this is the topic of discussion today. I am taking up all the things which are required for you to be a successful developer of software or a solution which are ARM based. Okay, so let us see what are the things you need to be considered, careful about. Understand the default compilation tool behavior. Okay, and the target environment. Okay, sometimes the compiler itself assumes something. Okay, because if you do not give anything specific to the hardware detail, then compiler cannot expect you to give that. So it will assume something and then proceed with some output. So that's what happens when you don't give any information for the tool. It may not be compilation or compiler or any other tool. So there are steps involved to move from a debug or a development build to a fully standalone production version of an application. So what I mean by that is, normally when we are developing any application or software using any processor based solution, we have a system, okay, target system, okay, board. So any software that needs to be running on this, first of all needs to be developed and debugged, make sure that it is working fine, then only it should be ported onto the actual hardware. Suppose you say there is a set-top box which is ARM based. Okay, there are buttons here and then LED glowing, and there is a hardware inside. Okay, which is ARM based solution. Okay, now power goes. So you will not be developing software on this system right away. We may have a development board which is given to the developer, software developer, which is similar to the target end hardware, production hardware. So the solution, whatever the set-top box software is developed, is run on this first on this development board, which is connected to a PC, a development platform. And then it is connected through a JTAG or serial debugger or any other interface that are there. And then download the software, verify it, debug it, run a debugger on this, and then make sure that everything is working fine. So this whole thing, maybe you may be tweaking the code also to output some values or write into some file or into memory. If you may be the actual software is there, and then you may be tweaking this hardware software to introduce some debug points. Okay, maybe put some printers, and then make sure that the complete control flow is working, and then the correctness is assured. Then we will be compiling and linking to the target platform. So this could be a restricted memory, or it may be a different layout altogether. So this software is to make sure that the debugging works fine. Most of the time, this new development platform and the original end target hardware are kept in the almost the same similar in terms of memory map or all those things, so that you don't have to make too many changes to the software or the tool configuration while loading the software into the end product, because we don't want surprises at the end. So we will do all the testing here and then put it to the system. So actually minor changes will be there between the debug version and the development build. So the development build is what a standalone running. That means when it is running on set-top box, it's not going to be connected to another PC, or developer is not going to be sitting by the side of the set-top box for it to work. It should work in the customer's premises without anybody or any developer by the side of it, or any the PC or anything is connected to it. So it's a standalone production version of the application. So first initially debug is done, and then standalone version will be generated. So some changes to the C library functions to be made to meet the target hardware. Okay, instead of debug environment resources. So C library functionality will now use the target hardware feature or LEDs or whatever, rather than the debug environment resource. It could be even if suppose printer has to be put, now there is no debugger running on the screen, so you cannot send it to a serial port or anything. So it has to use all the hardware, all the resources in the set-top box. So that changes the C library also has to be modified. Okay. The toolchain has no inherent knowledge of memory map of any given target. So normally, not normally, always the toolchain is developed for a generic hardware. Okay, generic memory map. It could be anything. The tools cannot be built for a particular memory map. Okay, the tools in the sense compiler, linker, assembler, whatever tools you see, they can generate any output for any kind of a memory map in the system. That means as long as it is within the 32-bit boundary, you can map the output of any linker or any compiler to any memory map as per your choice in the target hardware. So initially the tool chain do not have any inherent knowledge. We have to feed that knowledge with some configuration parameters. It means tailoring the image memory map to the memory layout of the target hardware. So we need to tailor the output of coming from the tools to meet the target hardware requirements. So an Android application must perform some initialization such as stack or heap initialization before the main application runs. So there is a requirement for initializing a stack. As I told you some time back, different modes of the stack pointers need to be initialized. So those kind of generic initialization, and then even the stack locations of different modes may be different for different kinds of a target. So before the application starts, there should be some initialization code which will be initializing the stack or the dynamic memory allocation, heap, starting address. Those things need to be initialized. So target hardware specific initialization routines are needed in addition to the ARM C compiler library initialization routines. So some things are very C specific, a language specific, like initialize something and then call the main routine. So that calling the main routine is very language specific. But target specific initialization needs to be done apart from the C compiler or C language specific initialization. So those library changes have to be done based on the hardware. Okay, these are the different considerations that you should be aware of when you are developing software. Okay, let us see. Now, what is semi-hosting? Let me explain. Full technical specification of the target hardware or memory map of the target system not available during software development. See, in a typical product life cycle, okay, the hardware design, okay, maybe we might have taken a decision that we are using on SOC, okay, but what are the kind of a memory which is going to be there, and then what exactly is the locations of the memory, okay, is mapped to which location of the address space. Those things will be coming up during the board design time frame. So board design happens sometimes later in the cycle. Whereas hardware specification and the software requirement specification, initially we will say product requirements, and then the specification is frozen and aligned with the customer, okay, and then the design starts. So design for the hardware and software also starts in parallel because to keep up the time to market. Okay, any product hitting the market in a shorter time will be able to attract the customer's requirements, and then it will be able to make some profit for the company that is making the product. So there's a fierce competition. So everybody wants to parallelize the development also. So software development also happens in parallel with the hardware development. Maybe the chip may be identified, or maybe chip may be getting done in the by a semiconductor company, okay, and they will be providing some device drivers and other things, and then the application software developer may be writing a application software even much before the even chip is made. So during the software development, the exact hardware specification or the memory specification, where exactly, or maybe rough ideas will be there, but it won't be very specific information won't be available. So full technical specification of the target hardware memory map is not available. So compilation tools have a default behavior. So easily to start with, when you want to test your software, just go with the default behavior and debug the application using the debugger and development of environment that we have. And then semi-hosting is a mechanism that enables code running on an ARM target to communicate and use I/O facilities on a host computer that is running on a debugger. So a semi-hosting is, it is not hosted fully on the hardware. It is not a standalone application. So suppose this is the hardware, okay, a board, a chip is there inside. So it is connected to a debugger. Maybe I'll call it as a PC. Okay. So part of it is running here. Debugger is running in this PC, and then the execution happens here. But there is some piece of some software here also, which is specific to the debugger, is there, so that it can communicate back to the debugger running on the PC with some information. So this is not exactly close, exactly a target hardware. Okay, it is not a standalone hardware because it is connected to a development platform, a PC, and a debugger is there, and then we are interacting with the, as a user, we are interacting with the hardware and then getting the responses from there. So it communicates using the I/O facility of the debugger. What I mean by I/O facility means, suppose there is a LCD display here in the hardware. Okay, LCD display. It is supposed to print some values here. But to start with, maybe while debugging is happening, all this output which is supposed to go to the monitor here may be coming to the debugger window, because the user is sitting here monitoring the output of what is happening here. Okay. So the user will be checking the code here and output coming from the debugger. So they don't have the complete target hardware also. So in that case, I/O facilities are used which are in the debugger. Okay. So when semi-hosting is executed, the debug agent suspends program execution. If we suspend the program running on that and then give a control to the debugger. The debug agent then uses the debug capabilities the host and the debugger running on the host is having. It is using that. So for example, printf output to debugger control. So the software running on the target hardware is suspended, and then control is given to debugger. And then you can say, if you are doing a stepping to the software, you will say that okay, breakpoint you will be putting, and then it stops the execution and then gives the control back, and then we will say that okay, run. Then control goes back and then it starts running. Then till the next breakpoint is there. Or step, if you are single stepping, then it will execute one instruction at the programming level. C program is there. The C program instruction level it will be executing some set of instructions here. So it is actually controlled by the debugger as well as the user who is debugging the software in the using the PC. So that is what is called semi-hosting. Okay, overview is this is the target hardware. There is some piece of library code which is modified to communicate to the debugger. Okay, debugger is on the host. This could be a PC or Linux machine, and then the output is put here, not on the target hardware. So this is the semi-hosting. Okay, rough understanding of this is the software running, and this is some debug agent sitting on the target hardware. In stopping the execution and then communicating with the debugger and then giving a control back. All these things will be happening. Semi-hosted operations work when application is being developed or debugged on the development box. So the application which is being developed is run on the hardware but debugged using the debugger here. Okay. So in the case C libraries, which are actually having the input output error handling and the stack heap setup and printf or writing to the hard disk or file, all these things are in the C library. They are also a little bit modified to say that it is connected to the debugger now. Okay. So conceptually, the C library can be divided into functions that are part of the ISO C standard. This is a completely C standard, and functions that provide support to the C standard. So these are all supporting functions. So this library is now connected to the debugger, and later on it will be only to the hardware. So that is what I said, that C library needs to be changed when you want to run the software on the hardware. Standalone mode when there is no debugger connected to the hardware. You cannot expect a set-top box at the user's premises to be connected to a debugging environment. So it is a standalone unit. That time this library will not be expecting that it is connected to some debugger. So we will be modifying it so that any error conditions, maybe it may flash an LED to indicate that restart the set-top box, or it will restart itself. Without user coming to know, or the user may not know what to do. So some erroneous condition, it may do some error conditions. It may send it to the service provider, and then it may restart, or it may expect the user to do something. So such things will be done. Okay. So the C library also will be modified for the standalone version of the software. When it is being debugged, the software which is set-top box software which is being debugged during the development phase, it will be modified to communicate with the debugging agent as well as the debugger sitting in the host. So this is called semi-hosting. Okay. So now, as a target is, as I told you, the tools are ignorant of what the image is going to be, and then we need to configure the tool to suit the particular target hardware configuration. Then there should be some awareness about the image, how it is generated. Image in the sense the code output executable. How is it generated by the tool, and then what are the inputs need to be given to the tool. Okay, tool in the sense it could be a linker or a compiler or a loader, whatever, and then so that the executable is generated properly, so that it runs on the hardware without any issue. Okay, even if you modify the hardware, you change the input so that the output coming will be able to run on the hardware. Okay, so let us understand the executable image. So don't get better. This is very simple if you understand the flow. See, else I told you embedded and linking format. This is the output executable format. Okay, that when we have multiple OBJ files, okay, OBJ files are to be linked. The linker gets multiple OBJ files to be linked to get an executable, output executable. So this is the flow, as I told you, as shown in the arrow. So each file, or even within the file, you may have different code functions. So there will be separate sections of each of them. Okay, this is a separate part of the program or code. Okay, I call it as program or code or text, whatever. There are execution regions are combined into some multiple execution regions. Okay, these are all execution regions, different execution regions, different input files are combined and then form an execution region, and they will all be in a different load region. I will explain you what is the load and then execution region a little while. So this multiple, this execution region will be of different load region, So they are put into the different segments. Okay, these are all output segments coming from them. Basically, the images generated is all binary coded instructions, but it's all combined. Multiple files are combined to form an executable. So when a big project are built, it is not written in one single C file or one single assembly file. Multiple C files, maybe multiple languages also used. Some C input, some C++, something will be written in assembly. So these kind of multiple kinds of files will be there to develop an executable. So this kind of multiple things have to be combined by the linker, okay, to get a final image file. So image file is the output, maybe I call it as a exe. So the linker may also get file obj file, okay, of different source file, or it may get some SO file, some stat object file, or some library file .lib or .s, some libraries, C libraries. So these kind of different sources are there. Finally, they form an executable. So you should know that there are multiple source files and library files combining into an executable. Okay, so there is a fixed header and structure is there to give additional information to the tool where to keep these images in the final executable. Okay, let us see some more. And one thing maybe you can remember, the 2 GB of program space can be there, but maybe the latest tool may have a different value. So you may have to look at the current documentation to know exact value of it. Okay, this is a program size. Now let me, what is the image structure? Number of its constituent regions and output. Okay, number of its the structure of the image is defined by the number of its constituent regions and output sections. As I told you, what is region? This is output section and region. So how many number of them are there? Okay, and positions in memory of those regions and sections when a image is loaded. So what happens is, in a typical hardware, okay, this I am showing the hardware like this so that you understand. This is the ARM processor. There is a flash memory. Okay, flash memory is there, and then there is a RAM chip. So RAM. Now what happens? Sometimes the flash will be having a code. This is called where it is loaded. The image is loaded in this location. It could be this flash memory can be mapped to some different address ranges. Okay, some address range, and then RAM will be some other address range. Okay, now this code may be copied from here to RAM and then run. So the loaded area will be different from the execution region. So it will be totally different physical location, physical addresses, because ARM has to access this to copy to another location. So it has to bring it from this memory to the register and then maybe copy it there, or it has to program a DMA to do that. But normally what happens is it is done by the processor to move the code from the flash to RAM. So there is a possibility that the loaded location, the memory where the image is loaded, may not be the place where it is executed from. Okay, that you should know. So the positions in memory of these regions and sections when the image is loaded, and positions in memory of these regions and sections when the image executes. So they can be same, they can be different. So you should be aware of it. Each link stage has a different view of the image. So when you are linking, you are creating a library file, its image will be different. And when you are executed file, when you are generating for a particular hardware, its view will be different, because it will be looking out. It is generating the image for what? Which hardware? What is the memory map of the hardware? Based on that, it will be generating the output. So it in different view will be there for the different stages of the linking. Okay, linker input. ELF object file. The object file is coming from the compiler. After the C source file or C++ source file is compiled and generated, an OBJ file is generated. So that is an input to the linker. And ELF object file can be relocatable file. That means the place where the memory where the particular code has to be executed is not fixed. It is relocatable. Means that you can move this code to any location, and then in one register you modify the address, the starting address of the location, then the rest of the code assumes based on that. Okay. So relocatable code is not fixed to any particular region or any particular memory. So relocatable file that holds stored data suitable for linking with other object files to create an executable or STAD object file. So That is one output. The output could be a relocatable file could be generating an executable file or a shared object file. What is the difference between this? Executable file is the final image which can be now loaded into some hardware and run, whereas the shared object file will not be running immediately. It will be loaded in some location maybe, but somebody else, any other program running may use this library. Okay, it is not an independent executable. It is sitting to be used by someone. It's a that is the name implies it is a shared object file. Okay, mostly a library file will be given as a shared SO file, which will be used by multiple processors. They will be used by multiple people. So the shared object file is not an executable asset individually, but it will be executed by some other processor. So an executable file holds a program suitable for execution. A shared object file holds a code and data as a following context. This context called a linker to process a file with other relocatable and shared objects to create another object. So shared object file can be used with some other SO object file or link file to generate another another executable or maybe another library. So you can keep on building libraries after library by using the SO file. So or you can generate an executable also. Okay. So maybe processing image. You could process image in an executable file. So that will be an independent executable file that can run on the hardware. Okay. So this is all very high level overview I am giving so that you are aware of what all different things you will come across. But when you are really developing software for a particular hardware, ARM-based hardware, of course, then you will have to read more about these tools and options which are there. Okay. My intent is not to give you complete information because it's very difficult to give it in a short time. Now, what are the shared object files? An object file is a definition found in the source file converted to the binary form and available for placing into a full program. So, what is the OBJ file is what a .c file, a compiler, okay, compiler generates a OBJ file. Okay, so it is actually whatever is defined in the C file as converted into a set of assembly instructions, converted into binary form, and it is all captured in the OBJ file binary form. It can be placed in the executable or it can be placed into a library, doesn't matter. So multiple O files are bundled together called a library. When you are bundling multiple O files and then forming a library, okay, you can form an executable or you can form a library. That means it is not a final executable. It has to be connected to another executable, OBJ file to form an executable. Then only it will be running. Or the library will be a static collection of functions. So you can create two libraries, static or dynamic library. What I mean by that means static library, typical, in ARM world, it is a .a extension, is linked to create an executable. The entire library is embedded into the executable. Okay, so static library is statically bound to the particular executable. Whereas in dynamic, a shared library is suffixed with S4, so that we call dynamic library or shared library or in DLL in Windows world. So it is called .so. It is analogous to the static library, but the shared library differs from a static library in one very important way. What is it? It does not embed itself in the final executable. So when the dynamic library is linked, the library stays alone, separate, and then executable is separate, and only when a particular thing is required, the library is linked to the runtime. So library may not be loaded in the main memory. What happens? Library may be in the static the secondary storage, and then whenever a function is required, it may be dynamically loaded into the memory. So effectively, dynamic libraries do not occupy or increase the executable size. So once the executable size increases, then the memory requirement of the executable in the main memory will also increase. So to avoid that, dynamic library concept is used wherever you want to reduce the image size. But you have to remember that dynamic library takes more time for that to be loaded and run. So that it does not embed itself into the final executable, and instead the executable contains a reference to the library and resolved during the runtime. So it is resolved at runtime, not even at the link time. Please remember, not at link time, at runtime. What I mean by runtime? When the executable is running, it will call a function which is in the shared object. or shared library. When the function is called, then it is interrupted, and the function, wherever that function is defined in a library, which is loaded into the memory, and then the control goes there. So based on the need, the library is loaded into the main memory. Suppose if that function is not called at all, then that library is not needed. So effectively, it saves the space required for the executable to run in the system. Okay. Now, what are the load and execution rules? Okay. See, I told you that load view may be different. That means the image where it is residing in the ROM may be at a different location. Okay. Especially the read write session is actually data area. As you see that read write is there, so is a data area. Okay, it is sitting in ROM because maybe initialized data, some values or some fixed values are stored. Okay, you may declare that constant, variable pi. Okay, maybe you declare a variable pi and then initialize it to 3.14. So this value has to be preserved and kept in the code. So those kind of values will be stored there, and then it will be put into the RAM, because sometimes you may be modifying the values also. The variable may be initialized, but it may be modified. So you may declare a global variable int count, okay, is equal to 100 to start with. So what is the value 100? It has to be stored here, and then afterwards we will be incrementing the count. So in that case, what happens? It has to be in the read write area. It cannot, the variable cannot be residing in the ROM area, and then you can increment it. You can't do that. So, but you need to keep it in ROM area, because this 100 will be lost, because the program will not know whether you are initialized with the originally in the source file, whether you are initialized with the 100 or 1000. It will know. It will not know. So it has to be in the part of the image. So the data which is initialized with some specific value may reside in the data area, and it is also part of the image. Okay, this is both are image. This is the code area. We read only. This is code. So this code can reside in the ROM and then you can execute, but data area has to be copied. But initially it will be in some location and then it will be copied to another location. So the load image will be different from execution image. And what is this section? You may have static variables which needs to be initialized to 0. So to save space of the image, the static variables or any variables which are initialized with 0 values, they are not kept here. But the information is kept somewhere in the image saying that these variables are in the occupying some location here, and then needs to be initialized with all 0. So those variables will be positioned here and then they will be filled with 0. So before starting the function, starting the application or execution, these things are done. So this particular area is copied there, and then another area is created in the data section, and then they are initialized with 0, so that when the function starts executing, these values are all in a proper places. This is all where the execution images are supposed to be residing, and they all reside in those locations. So that is what linker has seen as an execution view. Okay. So load view image region and section in terms of the address where it is located in the memory before execution, and execution views describe the image region where it is located during the image execution. When execution happens, where this data area and the initialized area should be residing, these addresses, they should be copied. Okay. So before passing the control to the application, this who does it, maybe OS or some other loader or some other software which is coming in between to perform this job before giving the control to you. So these are all already built into the executable. So it has to be done before this control goes to the main function or whatever. So this based on that, these things are done prior to the execution of the function. So, linker view. The linker has two views. As I said, the address space of a program which becomes distinct in the presence of overlay. Okay, let me explain this later. Position independent or relocatable program. I told you that a program can be relocatable. That means it can be put anywhere in the memory and it will be able to run. Okay, program fragments could be code or data. The fragments could be code or data. The load address of a program fragment is the target address that the linker expects an external agent such as a program loader or dynamic linker or debugger, okay, to load from that location to copy the fragment from L file, and might not be the, so the job is to, this may not be the address at which the fragment executes. So the loader load address is where the data or code area is residing, as I showed you earlier. And then a loader or a debugger or a dynamic linker copies to some other location before executing. So that is what is done by that is the difference between load address and executor address. So load address is where the code is residing. Execution address is where the code is or data is supposed to be there when it is executed. So let me see what is execution address. So program fragment is a target address where the linker expects the fragment to reside when it participates in the execution of the program. So why am I bringing linker? Because linker is the tool which does this locating these variables or the initialized data or the code according to the load area or executable linker. Okay. So if the fragment is position independent or relocatable, both are same. Its execution address can vary during execution. So the code, the relocatable code or position independent code can be put anywhere, and then you will be able to execute it. What is an overlay? An overlay is one of the two or more pieces of code or data that can be loaded to a predetermined memory region on demand at runtime. See, memory is very premium in normal case. Okay? As I showed you, shared object is one example where a required code is brought into the location before it is running. Another example is the overlay. That means this location, okay, some location in the memory is reserved for multiple OBJ files. Okay, it could be a OBJ or function. So based on what function is being called, okay, that particular function is brought into this same location. Okay, so all these OBJ files are compiled for or is positioned to be located into the same location. Okay, but not all the images can be residing. So one example could be that suppose you want to generate image file, okay, from it's a video image or a image file. There may be different formats are there for the video images. So we may have a encoding mechanism for different formats. The functions can be the different files can be loaded. Okay, then a.obj, b.obj. These are different formats. Okay. But based on what output the user wants, okay, the video output format, maybe one of these things needs to be the code has to be put in this particular place, and then the encoding has to be done. So we don't need to bring all the encoders into this memory area because the input format is converted into one of the output formats. Okay, so based on the choice of the particular program while running, it will bring the particular thing to run. So this kind of one or two more pieces of the code can be kept in the same layer. So we are overlaying a different functions into the same area. That's called overlay. So initially, each overlay is stored in RAM or flash, just like ordinary code data. During runtime, an overlay can be copied to a known address in RAM and executed there. So different encoders may be lying in the ROM, but only one encoder will come to the RAM and then get executed. This can later be replaced by another overlay when required. Okay, only one overlay can occupy that space in RAM. So you don't need to convert to multiple formats. You will decide to convert from one format to one of the other formats. So this is the input format. Suppose output format could be multiple, but it will be one of the output format. So once it is chosen, that particular encoder is brought into the memory in the RAM and then executed. So only one will be lying at the memory at any time. The compiler and linker provide no other special support for overlay. So compiler and tools will not do. Overlays are not automatically copied to the runtime location. So who decides it? The function which is running here decides which overlay function to be called. Because it is very specific to application. Which application? It only will know which loader, which encoder has to be called. Based on that, you will know which OBJ file needs to be copied into the RAM. So that is done by the executable or the application, not the tool. So overlay manager is a part of that program. The programmer must write extra code for a overlay manager that requires copies the required overlay to execution address. It also records which overlay is in use at any one time. The overlay manager will run through the application and will be called whenever overlay loading is needed. So for instance, the overlay manager may be called before every function call, which might require a different overlay segment to be loaded. So different based on which encoder is required, that will be called. Why am I saying this? Because you may come across this overlay manager, you may have to use in your system because of the restriction in the RAM. See, if the overlay is not there, what we should do? Suppose three formats have to be supported, all the encoders have to be copied in the file in the RAM. So it is a wastage of space because you are going to only encode into one of the formats. So why do we have the images of all the encoders into the memory? So it can be in a ROM, okay, or a flash, and then because that is cheaper, so you can bring only when it is required that particular encoder. So that will be done if you have a overlay manager with you, okay, which is running along with the application. So you may have to use it in your system. So better be aware what it means so that you will be able to use it whenever you are developing your own solution. So it must be ensured that a correct overlay segment is loaded before calling any function in that segment. So before any function is executed, a correct encoder has to be called. Otherwise, there will be a runtime exception. The same is true for data overlay also. Okay, so with that we are completing something on the tool. So let me look at the explain you some memory map related things. So I'll give you some higher level overview of each of these so that you understand how internally the tools are arranging the different segments or different type of the executable. The code is here, data is here, this is called read write, and then this is zero initialize. Okay, I have mentioned it here. So this is the normal order. Starting from the lower address, the tool, if you do not give any specific location for any of these images, then it will automatically place them one after the other. That means if suppose it takes 2 kilobyte of space, after 2 kilobyte, maybe this will be positioned. It may take maybe 5 kilobytes. Okay, normally data area is likely to be more than 4 areas. So after that, maybe initialize 1 kilobyte of data area is initialized. So this will be put. Now, what is the requirement of stack and heap? That is again the programmer has to say how much is required. So it will allocate space so that the stack is always going downwards, and then heap will be there. When will the heap be used? Like MLR, okay, or new. Those things will be getting the memory from this heap location, and then whenever free or delete is called, they will be released back to the pool. So some memory is got used by this function any user, and then once they call free, it goes back to the pool. So that is the heap location. So it keeps on growing up based on the free and usage sequence, and then the stack will be going down whenever a function call is nested. How many nesting of function calls are there, as much that much of stack will be used, as I shown you in the last session. How stack gets grown whenever a function is called. So it will go down like this. And please make sure that they don't overlap with each other. If it overlaps with each other, there will be a crash. So there will be a stack limit checking will be there as a part of the code, so that this kind of runtime problem don't occur. Or in the embedded system, the stack limit checking will be time consuming. So there should be profiling should be done before the choice of stack size and the heap size is done, so that during runtime at any cost, this will not overlap with each other. It should not overwrite it on each other. So if an image where a memory map has not been described, the linker places the code and data in this order. The linker decides this sequence. Okay. Now the image is linked to the load and run at address this. Okay, it could be changed. Okay, default it may be images read only and zero initialize sections are there. The heap follows directly from the top of this. I is explaining what I told you in the last question. Stack based location is provided by semi-hosting operations. Okay, the where the stack is starting, that is decided after the stack starts going downward. Okay. Now location of code and data. See, this is the read only. Could be a code and data also. How data can be in a read only? It is possible. You may define a constant data. Okay, constant int pi is equal to pi is not going to be changing in any time, right? You may declare some floating point constant and then initialize it as a const. So once you define a const, it will lie in the ROM area because that cannot be modified. So those data area also can be in the ROM area, that read only area. It's not ROM, need not be ROM, but it's a read only. Okay, the region will have a read only access. Okay. And then we have a data which rewrite and then zero initialize data. So how it is coming? It is coming from this file. Whatever your constants you define here, whatever constants you have defined here in this files, the file 2 and file dot c file has been generated into O file, and those constant values will be finding a place here. And then the code area of this and code area of all this will be coming into this. So A is this, and B may be from some other file. All the code area will be here concentrated. So every different files will be there. Each file you may define some global variable or static variable. So those variables are all collected together and perpetuated in one place. And then you may be defining some functions in each of the files. Okay, these are all different C files. Okay, they all generate obj files, .o file. Okay, so everywhere whatever code is there, that code and all the code is collected and kept in this. All the data is collected and kept here, and any initialized data is here, and all the uninitialized or data will be here. So the collection of all of them is done by the linker. Okay, from different obj files. So it has to link all the group all the relevant information, code, and then all the data area, all the global area, or the static variables, everything. They need to group them all and then put it in a proper place. So linker observes a set of rules to decide where in memory the code and data are located. Okay, they follow this sequence. Generally, the linker starts the input section by attribute, by name or position. With what are the file names? Maybe in the increasing order. This is alphabetically, this comes first, and then this comes next. So all the code belonging to this will be coming first, and then the code belonging to the next file will be coming next. So like this, it will be ordering the code in the final memory, because finally whatever functions you have defined, they need to reside somewhere in the location in the memory. So how the linker decides is what I am explaining here. The fully control the placement of code and data, a scatter loading mechanism is used. If suppose if you want to say, I want this particular code to be in this location, I want this data to be in this area, I want this code in the file should be in another area in the memory, then we have to use a scatter loading another file as an input where you can configure it. So this is a typical example where you may say that one region, my region, is starting from here, and then it will address this length is this much, and then it is up, it is holding all the read only component. That means code, okay, code or initialized data maybe read only. So that of this particular file, obj file, needs to be kept in this address. Okay. Then what happens? Whatever you have written in program 1.c, that code area, code, whatever function, suppose you declare a function f1 and then you define that output file, that obj file of that will be that function will be here, residing here in this location. Okay, starting from 0, location. So you can control it. Earlier what I shown was the tool decides where to place them, but once you define such a elaborate definition and then give different region value names and then different files, then it will group all of them according to the requirement that you have mentioned. So the tool, if this input file is not given, then it will do its default mapping. Otherwise, you will be able to control it. You should be aware of this so that when you are developing a software for a particular hardware solution, you will be able to position the code wherever you want. Suppose you want to keep the ISR routine in the lower 00 address, okay, 002 to 1000, whatever. And then in that case, what you want to do, you want to say all the ISR routines are written in this particular function, and then you say in this file, and then you say that this particular OBJ file needs to be placed here. Then all the ISR routines will be residing in that particular memory. Okay, very good. So scatter loading description file is shown above. The region is defined by the header tag that contains the minimum name for the region and the start address. The length can be another attribute. Okay, maybe you can mention about this kind of exercise also. Okay, that region. So accordingly, the multiple regions of the pages, okay, wherever it is residing, that page region will be, the page access permissions will be defined. So API access permissions will be defined. Okay. The contents of the region depend on the type of the region. So what type, .ro or RW, okay, you can define any of this type. Okay, sorry. Okay. Now, what are the type of simple images? Type on image. So is just a different image can be there. So RO, this is the RAM, okay, and this is a load view and this is execution view. Just this, while this is the view of the program when it is not executing, and when it has to execute, this has to be created. Who does it? It could be the loader or debugger or the you have to write some code, as a part of the library routine to copy and then initialize the values to all zeros and then give a control to the function. Then during the execution time, this should also be there. But during the load time, when the image is kept in the ROM or RAM, this may not be there. This will not be there. This is called a load view. 3 contiguous regions of execution. This is it is shown as a contiguous location. Another image is this will be in a separate location and this can be in a different places. So they can be contiguous. It's shown as contiguous. It could be in a non-contiguous place. That means this section can be somewhere else. What is the advantage? Suppose you don't have a memory in a contiguous space, you are not mapped, then these images can be created on path to be executed at a different location and it can be copied there before the execution starts. Okay, but it could be kept in the ROM in a different locations. Okay, different addresses. This will be mapped to some address in the hardware. So ARM processor, when it wants to actually copy this section into this, it has to access this first and then copy there. So that will be done. So that for that to do, it should know this location it is mapped to, this address, this address. So the linker would have positioned the load view here, the code will be here, but when it is moved, it should be executed only after moving the data area here and then it will be executed. Okay, this is called 3 contiguous space load view, 1 region for load view because this is all contiguous in load view. Okay, another one is load view itself having 2 regions. That means this will be in a separate location, this will be in another region. Need not be contiguous. Okay, some gap may be there, and here also there can be gap. 3 contiguous, non-contiguous locations may be there. So these are all different images which are supported by the ARM linker, and based on the target hardware, it can be done. So how do we start the application? Default initialization sequences before the main function is called of any user code. The C library is called. Okay, it will copy the code and data as I told you from load image to the execution image, then decompress. So sometimes what happens is 1 second, I am going back to I didn't tell you this decompress. That means while it is kept here, it will be in the compressed form, and then it is decompressed and then kept it as if the execution image, how much space it occupies, that will be there. So it may be you will save some time in the space in the ROM. Okay, so sorry, so it has to decompress. So before giving a control to run, this will be done by the library. So copy and decompress RW data, initialize the ZI data to zeros, and then set up the application stack and keep, initialize library functions, and then maybe call some top level constructors, and then the control goes here, and then exit is called or is terminates, it will come here and exit from the application. So it has to undo some of the things. Okay, maybe release some area, some memory, and then we give a control back to the OS or any other operating system running in the system. So this is the default initialization sequence. So before any application runs, so much of job has to be done. Okay, so it is when you develop a software and run in your system in a debugger, it runs immediately. But when it has to be done on target hardware, there is a lot of things involved. That's what I'm trying to tell you. So you should be aware of these things when you are developing software for a targeted hardware. So in most embedded systems, initialization sequence is executed to set up the system before the main task is executed or called. Okay. How do you debug it on a target hardware? So what we do, typically we will be debugging it on a semi-hosting support, but once we retarget it, you may have to move whatever images in some memory to some other memory here, and then the C library functions also to be modified because it has to use some of the hardware specific printf or some LCD monitor, the display. It has to use some of the features which are resources which are there in the hardware. It can't assume that whatever debugger is going to be running on the other side. So retarget it means you have to recompile the at least the library portion, may not be this portion, and then build the executable to run it on the target hardware. Okay. By default, C library uses semi-hosting to provide device driver level functionality, enabling a host computer to act as an input output device. This will be acting as input output device. Finally, in target hardware, this target hardware will be taking care of all the input outputs. Okay. So that has to be done. It is not that whatever you debug here, the same image will run on the hardware. There will be some changes. Now I have told you what are the possible changes, what are the initializations to be done, so that you will understand. It is not that it is, you can just download it on the hardware and it will run. You have to do a lot of work before that. And you have all the knowledge now, how memory is mapped, how cache behaves, how MMU behaves. So you have all the knowledge, and once you have a tools documentation with you, you will be in a position to perform, develop any software, and then debug it on a semi-hosted environment, and then retarget it, make modifications to the library, and then run it successfully on the target hardware. That's where you will be completing your accomplishment. That means whatever all the things what you learned will be in use once you start working it on the target hardware. So this is bringing us to the end of this section. We have completed all the discussion that I wanted to cover on tools and library in linker in particular, and then some memory map, and then how different memory maps changes from target to the development platform. Okay, so I hope it was useful, and I really enjoyed sharing this information with you. And wishing you all the very best for wonderful development and working with real hardware. And from the next lecture, we will briefly touch upon the AMBA portion, the specification, the system bus specification, and then some peripherals we'll see before we conclude the lecture. Okay. Wishing you all the very best. Thank you for the time and attention. See you in the next class. Bye bye.